Hello, this is my video for the Aeronautical Engineering Challenge, and this is my aircraft. It's based after the SJ-71 Blackbird, which was one of the fastest jets ever created. And now we have to make a glider for this, but I've made something that's more or less not a glider, and is better at just getting at a rather high speed and then kind of remaining that until it gives into gravity. So I'm going to show you the test flight. Ground control, get ready to record. Start now. Hello, it's me again. This is probably going to be the final attempt. We've done a lot of upgrades to the plane. As you can see, it's got a much wider wingspan and a bit more area, and we've also cut down on the weight on the back. There are some fatal flaws in the calculations, like we needed a lot more area on the wings. I didn't take into account the velocities we were actually going to be able to get it to reach, so hopefully this design is going to be better, but it might just be a bit hard to see. So, that's bright. That's further than what we've ever got. Do you think we should just use that?
Yes.
One final adjustment that actually worked better. So from what you would have observed in the clip, a lot of failure, but some joy and success. The original plan was not calculated properly. It didn't have enough area or length of wing, and that ruined parts of it, but it did go rather far at the powerhouse. It just didn't look elegant, and that annoyed me. And there were just some key principles that I just didn't take into account, like the weight distribution, and it was a lot heavier to the back, and that really stuffed it up and made it do loops. So, over the time I have free, obviously not for the Griffith University challenge entry, but for just in my own time, I'm definitely going to upgrade the model, put some heavier materials in the fuselage, and maybe even upgrade it with a little jet at the back using, some potassium nitrate, and maybe create an exothermic reaction that blasts out. But definitely do the math before I do that. My issue with doing the calculations earlier was that from what I saw on the NASA website, for the glide calculations, as seen here, you needed to already know some key factors, such as the distance it went, the height in which it travelled. You needed to know the lift coefficient. You needed to know the actual lift, because to get the lift, you need to know that the lift is equal to the lift coefficient times the air density times, I don't even know what I wrote there, times, oh crap, that's what I forgot. Times something else squared, divided by 2, then times the wing area, which is what I failed on. Then to get the weight, that's the lift times co of the glide angle plus the plus the drag times sine of the glide angle. Yeah, and the drag is then equal to the lift of sine of the angle, which is equal to the drag time. Yeah, so it all basically needs experimental data first, which is interesting. And then, but generally, one of my mathematical statements did tend to hold true. This generally works, because if the velocity and acceleration is not equal to this specific value, it will equal in a change in distance, equal to, your normal distance equation, the initial velocity times time plus 1/2 times the acceleration times time squared, and the change in y, which would equal to the sine of theta times t times 1 divided by 2 times the acceleration in the x direction times t squared. So basically, I'm going to do a lot of work on this and make sure next time it's exactly how it needs to be. But generally also at the end, to get it to work how it did, we basically just ripped the longer wings off, and it actually worked better because the weight was more equal. So if I had the time to do that at the powerhouse, it would have been much more effective. But I hope this was an intriguing video and my angry rants weren't too annoying. Thank you for spending your time watching this.